Hello everyone and welcome back again. Today we'll start looking on the sieve analysis test of the aggregates. And before this one, we need to do a recap of the previous session that we studied the grading of the aggregate. We discussed that we have different grading of the aggregate, that the aggregate that is range between 4.75 millimeter particle size and can go up to 20 millimeter particle size. And in this range, we might have different scenarios and different grades that the aggregate can be either single graded aggregate or well graded aggregate or gap graded aggregate. So the question here that's if I have a sample of the aggregates and the aggregate particle size of the aggregate is range between 4.75 as a minimum particle size and the maximum particle size is 20 millimeter. So the question is, how do I know that this sample is single graded or well graded or gap graded aggregates? How do I know the grading of the sample aggregate in my site or in the sites? So in order to know the grading of the aggregate of my sample, we need to do the sieve analysis test. This is what we will start today discussing the procedure and the steps and how sieve analysis test is done in the lab. These tests should be done in the lab and we'll start learn the equipments, the procedure, and the test. So as I said, the purpose of the sieve analysis test is to know the existence of the aggregate particle size that lies in the range of the aggregates. So the general idea of this one, we are using different sieves. Here we are using different sieve with different sizes. The sizes of the sieve itself. We have a sieve with big size or big diameter and smaller, smaller, and smaller, smaller. So the idea in general that we list or we put the sieve from the big sieve and the smaller with the smaller and smaller and smaller. Then we add the sample particle size here and we start to shake and we start to some of the aggregate will go through, will pass this sieve, and the particle size that has higher than the sieve side, it will retain on the top. The same here, it will go for the smaller, and the bigger particle size will retain at the top, and the smaller will go and pass the sieve. Then it will go for the following sieve that has a smaller size. And some of the particle will go past this sieve and some will retain at the top. The same will go for this one and this one and this one. So it will arrange from the bigger sieve size with the smaller and smaller, smaller until the end we have a pan with zero diameter. So this is in general in order to know how much particle size or how much particles that is retained on each sieve. So this one will help us to know the quantity of the particle size in each sieve. So it will help us to know the quantity of the particle size here in each sieve so we can know the particles here, the distribution, if we have good distribution of different particle size in this range or not. So this is in general how it looks. So this is an example how sieve analysis test and procedure is done in the lab. And you need to know that sieve analysis test or the grading of the aggregate is done for the coarse aggregate as well as for the fine aggregate. For the gravel, the big stone, and also for the sand. For the gravel, we might have these different scenarios, the single, well graded, gap graded, aggregate, coarse aggregate. The same, we might have also single, well graded, and gap graded sand or fine aggregate. So today we'll have an example of how we can do the grading analysis or sieve analysis for the sand or the fine aggregate. Both of them, the same procedure, the same idea, how we can get, and we'll have this table, and this is table represent the process and how we do the calculation. We will start to do the calculation step by step. So starting this test, starting with listing different size of sieves, starting from the big, smaller, smaller, smaller diameter of the sieve size. Since we are using for the sand, and we know that the maximum size of the sand is 4.75. So the maximum sieve or the higher sieve size, it should not be more than 4.75 because the maximum is 4.75. So the maximum should not be, or the higher sieve should not be higher than 4.75. So we have 4 millimeter sieve size starting here, the highest sieve. Then we'll go with the smaller size sieve, which is 2.36 millimeter. Then we go with the smaller 1.18, 0.6 millimeter, 0.3, 0.15. So what is this number? This is the sieve size. This is the diameter of the sieve itself. The higher one is 4 millimeter. Then we'll go with the lower one, 2.36 millimeter, 1.18 millimeter, 0.6, etc. So we'll both or list the sieve. We arrange the sieve from the big to the small. This is the first step. The second step is to weight a specific amount of the sand or the fine aggregate. Let's say 1 kilogram. We bring 1 kilogram of the sand and we put it on the top of the sieve, the highest one, the one at the top. Then we start shake. We use actually a shaker machine. This shaker machine help us to shake, and it allow the particles to go through the sieve itself. So we put the bigger or put the 1 kilogram sample of the sand on the top. We start to shake. So as a result of the shaking, some particle, the smaller particle or the particle that has particle size that has lower than 4 millimeter, it will pass through the sieve, and the particle size higher than 4 millimeter will retain at the top. The same go with the smaller one here, 2.36 millimeter, and the particle size that has higher than 2.36 millimeter will retain at the top, and the fine aggregate with a particle size lower than 2.36 will go and pass this sieve, and will go with the following sieve that has a diameter lower than this one. So here also the sand or the fine aggregate that has a particle size higher than 1.18 millimeter will retain at the top, and the sand with a particle size lower than this one will go and pass the sieve. We'll go with the following one, and the same goes for the list. So we will start to do this process, shake, in order to allow the particle either go through this one or retain on which sieve. It will retain in each sieve. So this is the first method. We list from the big to the smallest. We put the sample, specific amount of sample, let's say 1 kilogram. We shake, then we'll start to see some particle will go through, some particle will start retain on each sieve. So the first column here is the mass retained and in each sieve. For example, for the first one, how much retain, how many among of these 1 kilogram of the sand, how many gram retain on sieve number 4 millimeter 0. So it means that all the particle size is went through this sieve. For the following sieve here, the sieve 2.36 diameter, this is 6.2. It means 6.2 gram retain on this sieve, and the other went through this sieve. We'll go with this sieve, the third one, 1.18 millimeter. The mass retain is 49.3 gram retain at the top, and the rest past this sieve. So we are trying to weight for each sieve how much or how many kilogram retain at each sieve. The same go for this sieve 0.6, the same go for 0.3 millimeter sieve. This is represent how many kilogram retain on each sieve. So we need to have also a balance in the lab, or require a balance in order to weight how much retain on each sieve. So this is the mass retained on each sieve. Then we start to convert it to a percentage. So this is the mass retained. We convert it to a percentage. The total, for example, the total is 1000 gram. So if we convert this one in a percentage, this one divided by this time 100, it will be 0.6%. The same goes for the all. We just convert from the gram and to make it in a percentage, how much the percentage is retained on each sieve. Then we do the cumulative. Cumulative is this one is the same here. Then 0 plus 0.6 is 0.6. Then 0.6 plus 4.9, 5.5. 5.5 plus 30.3 is this one. Then we will have this, what we call it, cumulative. And at the end of the cumulative of the percentage, we must have 100 here. But because we need also to have the band, because we also have a particle size. Some of the particle retain here, and some also passed through this sieve, and it went through the band. We call it band. So the band is the rest. So we also need to have another arrow here represent the band. So that's why it doesn't. In this here, we will have a 100%. So this is the retain cumulative. This is the percentage retain. Then this is cumulative retain percentage. And this is the cumulative passing. So how to calculate the cumulative passing is this is 100 minus the retain cumulative passing. So it means 100 minus 0. And this one is represent 100 minus 0.6. This is represent 100 minus 5.5. This is represent 100 minus this number. And this one is 100 minus 78.2. And this one is 100 minus this number. So we can get the passing cumulative percentage. So this is the table that we should follow and do this calculation. In order at the end of that one, we need to know the passing cumulative percentage for each sieve. Starting with the gram, then we convert the gram to a percentage, then we do the cumulative of the retain, then the passive cumulative 100 minus this one. So what I need this one, and I need this one. So these columns, then I start to draw the relationship between the sieve size, this one, and the passing cumulative percentage, this one. And so this is the drawing. This is a relationship between the passing, this, and here is the particle size in millimeter, this one. Then I start to draw the relationship. I will get these as scale. So for example, and here it will be better to get the logarithmic scale here. It will be much clear for you, and this is the most common scale that we need to use in this sieve analysis test. It's better to use the logarithmic scale in order to have this as curve clear for you. So starting with here, the sieve analysis 4 is 100. So you know how the logarithmic scale, if you don't know, this is 0.01. This is another one is 0.02, 0.03, 0.04, 5, 6, etc. And it will go up to here 0.1. This one will start 0.2, 0.3, 0.4, 0.5, 0.6, 0.9, then 1. Then this will be 2. This is 3, 4, 5, 6, 7, 8, 9, 10. Then we have 20, 30, 40, 200. Then 200, 300, etc. This is the logarithmic scale. So based on this one, we start to draw the relationship between the sieve size, this one, and the cumulative passing. So starting with 4, at 4, where is 4? This is 1, 2, 3, 4. This is 4. At 4, we have 100%, so it will have this point here. 2.36, where is 2.6? This is 2, this is 3. 2.36, it will be somewhere here, and it will go up at 99.4. So this is 99.4. Then we have 1.18. What is 1.1? This is 1, this is 2, this is 1.5, this is 1.18. It will be somewhere here. It will go up in the value of 42, so 44. So 44, we have this dot. Then we have a 0.6. What is 0.6? So this is 0.1, this is 0.2, 0.3, 0.5, 0.6. So this is a 0.6, and 0.6 will go up. What is the value? 64.2. So this is 60, it's 60, this is 65, 64 will be somewhere here. So if we go here and we get this dot. Then we have 0.3, 21. So where is point T? 0.3. So this is 0.1, this is 0.2, and this is 0.3. This is 0.2. So this is will be 0.3. At 0.3, what is the value? 21.8. So 21.8, this is 21.8 will be somewhere here. So if we draw the line here with this one, we will get this point. 0.15, 5.4. So what is 0.15? This is 0.1. This is 0.2. 0.15, it will be somewhere here. And we will go up 5. So this is the 5. We draw, we get this point, etc. Then we draw the S curve that passes through all these points. So this is after all the calculation, after all the process, I draw this one. Then we still didn't get, because the purpose of the sieve analysis is to know whether we have a well graded, single graded, or whatever. So after drawing this one, so what I'm getting, I just get this as curve. So based on this S curve, or the relationship between the passing and the sieve size, we start to know whether it's well graded, poor graded, or gap graded. How do I know? Based on this one, based on standard. The standard gives you the lower limit. So this is this is the limit, this is the minimum, and this is the higher limit. So if we draw this one and we see if it is lie in this range, between these two lines, like if I have my S curve lies here, or the S curve is something like this one, or something like this one. So in this range, in this area, if the S curve is lies in this range, it means it is well graded. We might have some cases if we might have S curve that is something like this, for example, which is not lie in this range. It's not in this range. Or we might have something like this that is far away the range of what we have in the standard. So this is for the fine aggregate, and this is the range for the coarse aggregate. The coarse aggregate, it must be like the SKs of the coarse aggregate sieve analysis. It should be somewhere in this range, which is written or shown in the standard. We might have coarse aggregate that has this range, which is not well graded. This is the well graded. Only the S curve that is lines between these two lines, the upper and the lower, in order to know it is well graded. So this is the range for the fine aggregate. So the S curve should be somewhere in between these in this area. For the coarse aggregate, also it should be the S curve between or lies in this one. If we had our S curve is somewhere here, then it is not well graded. It means that it can be either poorly graded or single graded aggregate. But the S curve that is lying in this green area or in this blue area for the fine aggregate, this is for it means that it is well graded. It means there is the existence of there is a good distribution for the different particle size for this one. Another thing for the fine aggregate that can help us in the sieve analysis test is the finance modulus. So finance modulus is another properties of the sand that can be calculated through the same process or the same table here, and it will help us give us an indication of how tell us how coarse and how fine is the sand by calculating the finance modulus. How to do the finance modulus? It's simply we use the same table, but the same table here that we use. And how to calculate the finance modulus? It says that the finance modulus is the summation of the cumulative return divided by 100. So this is the cumulative return. We sum all this one plus 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 plus, we get this one. So this is the summation of the cumulative return. We divide this number by 100, we can get the what we call it finance modulus. So what is finance modulus? Finance modulus, it means it give us, after we getting, for example, it is well graded. It means that there is a big, smaller, 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 smaller. there is existence of different sizes between this range, the maximum and the minimum of the aggregate. And this number, it tells us, for example, the first sieve is 0.15, then 0.3, 0.6, 1.18, 2.36, and the sixth one will be 4 millimeter. Here we have 0.4, 0.15, 0.3, 0.6, 0.15, 0.3, 0.6, 0.18, 1.18 is the same. So we arrange this one from the small to the highest, and we name this one as a 1. This is 1, 2, 3, 4, 5, and 6, etc. And this one, 2.18, it means it lies between 2 and 3. 2.18, this is 2.18, this will be somewhere here. So it tells us the average of the particle size. So the average of the particle size is lie between 2 and 3, between sieve number 2 and sieve number 3, between zero point 0.3 and 0.6. So majority or the average particle size is somewhere here for the stand or the sample of what we are doing the test for. So this is actually the how sieve analysis works, how to calculate the finance modulus of the sand, and how we can go through the steps and do and determine whether the aggregate are using, whether sand or gravel, is it well, single, or gap graded. And this is the process of how we do the calculation, how to draw it, and how to get the S curve, and how to determine based on the lower limit and the upper limit whether the S curve is lies in the range of the well graded aggregate or not. So we stop here and we see you in the following